A very good evening to all the members who have joined for 93rd IIRS Outreach Program on Geoinformatics for Biodiversity and Conservation Planning. So I welcome you all. Probably today it is the sixth session of the um, outreach program, and the topic for today is cloud computing for forest monitoring. So I hope you all can see the slides. So basically, for doing the forest monitoring, we first should be able to see the maps and be able to map the forest cover, whatever we are analyzing. So I've slightly changed the uh, uh, topic of the presentation to forest mapping and monitoring using cloud platform, and we'll be seeing some application of some machine learning for the same. So I'll move on with the slide. Yeah, so this is the basic outline for today. We'll be having a look at what is cloud computing, what are the types, basic types of cloud computing, what are the benefits, and what is the exact need. Why do we want to, imply cloud computing into field of remote sensing? Then we'll have a look at the something called Google Earth Engine, which has a very crucial role these days, which itself is an example of a very popular cloud platform these days. And then we'll see a hands-on, we'll proceed and we'll see an actual implementation on the Google Earth server. Maybe all the other participants can also try at the same time while they're attending this lecture. Yeah, so what is cloud computing? So we all know the word cloud itself means the hub, a network or a network of networks. So basically, in today's modern world, we all are aware and we all are using services which are, directly or indirectly coming from the. We are using all the resources in form of services, like we use internet on our mobile phones. It itself is a service. Then we use certain applications, whether it is accessing our mail or it's a social media mobile applications. All those applications we are able to use based on a cloud platform. Yeah, so basically a cloud platform is a virtual implementation of all the hardware and all the software components of a system. So they are being implemented at a remote site, which are not directly in close vicinity with the user. So that is basically the idea of a cloud. We'll move on. Okay, we'll have a look at what are the cloud computing structures. So basically, what are the forms in which cloud in a conventional way works. So there are basically three types of clouds, which probably many of you will be knowing: public clouds, private cloud, hybrid cloud. So public cloud means we all are aware of EC2, Amazon Elastic, Amazon AWS services, which are providing as public cloud. Then Microsoft Azure. They are the examples of public cloud. So and when we go to private cloud means there will be the implementation is basically for a particular enterprise or a particular group of individuals or a particular company or a organization. So their way of implementing becomes a little private to that enterprise. Then there is a third setup called hybrid, where it's a combination of both public and private, where maybe the infrastructure related to the central servers or physical servers may be done at the enterprise level, but all the services and resources will be provided as a virtual network to that particular company or organizations or the individuals who are involved in that organization. So these are major three classification of cloud computing structures. Then the types of cloud services. So basically the main idea is basically cloud acts on a simple idea of a thin client. Thin client means conventionally we use, whenever you wanted to purchase a desktop system or something, we had to purchase processor and we had to pay for storage and RAM and all the maintenance stuff we purchase at our own site. But what happens when you become a part of a cloud service? There are three forms in which cloud is giving the service. First is infrastructure as a service. So basically you don't have to buy a very costly hardware. You just need a thin client, all other. And what cloud will do, it will create a virtual machine. The cloud has its own central implementation somewhere of physical servers. There they'll be creating the virtual servers, and you will be assigned a virtual machine which will be acting as a real machine to you. So basically all the infrastructure which you would have otherwise needed to set up at your own place, you get it as a virtual machine. Now, platform as a service. So when you get a virtual machine, you basically use a thin client. The thin client could be a thin client could be a very minimal accessories, a laptop with a minimal accessories, or a thin mobile phone with the very least hardware support. So with the virtual machine, you'll be having some operating system. You'll be needing certain operating systems because you may be certain, or you may be working with part of some applications which need some basic software installations on the virtual machine. So in that, basically you get the OS level. So platform means that platform for your essential services will come on that virtual machine, and you'll be able to use your applications. And third component is software as a service. Basically, you can use your software on that platform, on that infrastructure, that is the virtual machine given by the cloud. So that is the basic idea. You can see the diagram also. So we'll move on. What are the benefits of cloud computing? So the benefits are really very self-evident that there is a lot on the user side. There is a cost benefit, like you don't have to purchase all the stuff on your own. You don't have to invest in the hardware. You don't have to invest in the maintenance of the hardware. You don't have to purchase the software or licenses. So that way it is a cost effective strategy. Speed, because definitely there are high-end servers, high-end hardware implementation done in the cloud central level, so that they can, because they're targeting a huge number of people to give their services. So they already take care of all these overheads like speed and efficiency and all that, global scale. So basically the reach of a cloud service is much more. And the performances are also affected because all the central data center, it will be taken care at one place, or physically it can be either at one geographic location or multiple geographic locations. So everything else is taken care at the central level. So there are a lot of benefits for the direct user of a particular service coming from a particular cloud. So the main question here is like, what is the need for cloud computing into the field of remote sensing? Or when we, so what happens basically, there is a huge number of satellites already revolving around the planet, and it has been happening for more than 4 or 5 decades now since the development of this satellite technology. So now what we have is, we have huge amounts of data which is already being stored from past, and there is already an ongoing process in which we are continuously getting the imagery and the digital data. So all this data is there for us. So it's very difficult for an individual organization or individual user or enterprise to host all this data on their own and do the further processing or whatever way they want to analyze the data. So in that sense, what cloud computing platform does is, it does a very wonderful work, is that it stores, not only it stores all the past historical satellite data, it also gives you other components along with that. It provides you a platform, it provides you tools to operate on that data, use it at the same time, do your analytical studies, and then you can save your work. So in that way, it is a very speedy and processing efficient method. So these are the various factors why cloud computing affects in a positive way to the remote sensing field. Yeah, so basically coming on to the Google Earth Engine. So Google Earth Engine is a cloud-based platform for geospatial analysis that brings Google's massive computational capabilities, just like I mentioned in the previous slide. So Google has created this cloud platform. So what happens, we'll be seeing in some next 1 or 2 slides, we'll be actually going to this server, Google Earth Engine code, and we can see that's how different data is made available there by Google, and how there are algorithms, how there are already default implementations and functions created there for a scientific community or for a layman user who wants to just have a look at the data and wants to do something with the data. So it's already ready-made functions and algorithms are made available on the Google Earth Engine. You can see in the diagram in the slide, that satellite imagery is available plus algorithms. Then using those algorithms and images, you can do your studies, and you can find out, or you can make your own studies about different topics related to the planet or related to a particular nation or geography. We'll move on to, yeah. So we have already covered what is the purpose of Google Earth Engine. So it also helps us, focus on global challenges that involve large spatial data sets, and different scientific communities. They have the access to their relevant data which they want and they want to work on, and they can proceed with their analytical studies. Okay, so basically, what are the components of Google Earth Engine? So as I mentioned, there are huge data sets available, whether it's satellite imagery or atmospheric data or geophysical data. Then there is computational infrastructure. So all the functions will, they will be accessing the resources from Google servers. So all the computation is being done at the server level at the Google. So you really don't need much of a hardware, heavy hardware setup or heavy hardware requirements at your end, at the user end, to finish these analytical studies in case you want. Then there is this application programming interface. So we will see in a moment of time, we will just see there will be an editor provided there. So wherein we can, actually write our functions or write our manipulations, whatever we want to do with the data sets available at Google. Then there are certain apps also which the user can create using the same functions available there. You can create your own geospatial apps also, and you can host it there in the Earth Engine. I'll proceed further. Okay, what are the data sets available? So these are the different data sets available there. Landsat data available in GE include reflectance data as well as various ready-to-use computed products such as NDVI and EVI. And Sentinel data is available, Sentinel-1A and 1B, that is SAR data. And then we have optical data also, Sentinel-2A and 2B. Ocean and land data for environmental and climate monitoring from Sentinel-3, and air quality data. So these are the examples of the data sets available there. These data sets include satellite imagery, climate and weather data, and geophysical data. So we have already gone through that. MODI's data is also there. And not only this data is available there, but all the temporal resolution is also there. Like a satellite sensor is, capturing a data every 6 days or every 12 days or every month, or so the data is being, acquired there temporally also, and it is made available in the Google Earth Engine. So here's a link also provided in the. If you want, what are the available datasets can be found at, you can click this link, developers.google.com, Earth Engine datasets. So basically this developers.google.com is a place where you can actually go and search anything and everything related to this Google Earth Engine, whether it's about datasets or whether it is about the actual functional implementations or related to algorithms. Everything is made available there in a very efficient and proper way. So it's a good help. So this is a chart. It shows what are the different data sets available. Like you can see, there are 4 to 5 columns: data set, nominal resolution, temporal granularity, temporal coverage. So temporal means 16-day, or you can see 16-day to 10 days on different Landsat satellite, Landsat 16-day. So every 16 days there will be a satellite image acquired by the sensor, and it will be hosted in the Google Earth Engine. Temporal coverage is from 2013 onwards, till present date it is still operational. And the spatial coverage is global, like on full planetary scale, this data is being acquired. So these are some of the data sets available. This is same way in the slide also. Okay, if anybody wants to practice at the same time, they can also follow these procedures. Procedure to access Google Earth Engine code. So I'll be going to the Google Earth Engine code right now. So if anybody wants to join, open the web browser, Google Chrome or Mozilla Firefox, etc., available on your laptop, desktop. People using mobile phones, it won't be possible for them. Log into Google account. Just make sure that you are logged in into your Gmail account. Or the third is, after you log in into your Google account, just open another tab in browser and type the following URL in address bar on top of the browser. In case anybody's attempting this, I'll just hold on here for 2 seconds. You can just type Google Earth Engine code and you'll get similar link there. So rest of the slides in this presentation are basically you can see this Google Earth Engine code editor. So this we can see actually live going to that screen. So most of the slides I'll be covering in the demo only there. So basically this is making aware of, so we'll actually see the live because going through the slides a little passive. So I'll just click this link now. Hopefully it will open. Okay, I already have this open here. Just a second. Yeah, so I hope my screen is visible to all. This is what a typical Google Earth Engine code screen will look like, right? So as you can see, there are components and draggable. So at the bottom, you have the huge map, like which shows everything. The full global map is available there. You can switch on to satellite map if you want, you can change the base maps. Mostly we prefer like, yeah, so this is currently it is somewhere near Dehradun. So this map is showing. So the bottom one is the main component where you can actually visualize all your maps you create or all your classifications or all your, your field data in case you have plotted here, you can visualize here. Then in the middle, right middle here, I don't know if I can use the pen. Yeah, this. Okay. So you can see this new script, right? This middle portion is for, this is the application programming interface, or you can simply call it editor also. There are certain buttons also provided here in the middle portion. Here basically it is for writing your code, whatever you want to write. Suppose I want to print hello, I'll just click on this run button here. So on the left hand side, you have this another component, console. It will print hello here. So this is a console. This task tab will display all the tasks you run here. Like you export some image or you download something, it will display here. Then this is the inspector. When you click on any point in the map at the bottom, so any information related to that particular pixel will be displayed here in the inspector. Point, longitude, latitude, zoom level, scale. This will be covered in this left segment. Then a very important component that is provided on the, this was the rightmost component. And there is a very important component provided on the left side where you can see there are scripts. And there are docs and there are assets. So docs are the ready-made functions. EE means like whatever is available by Earth Engine. Algorithms, these are the algorithms. Then there are, fill, minimum, match, clouds, all these functions. Depending on your study and your utility, you can utilize array for handling the data or storing. So block, classifier, cluster, date range, and there is something called a map which we are going to use extensively. This map category is provided by the Google Earth, and these are the functions. See, map.add. So you can read the description also. Adds an item to the map, and then that map will be visualized. So while we'll be having a look at all these things, right? All these functions are made available. You click on it, you will get whether it requires any arguments or not. So this is a JavaScript API. I'm sure many of you will be already aware with this. So these docs is everything on the server side which is provided, which you can utilize. Now scripts is something which a user owns it. Like if you are logged in, whatever scripts you have had, like for this because of the limitation of the time for this session, I have pre-saved scripts. Like these are the scripts. Like if I click, suppose I want to click this one. Yeah, Yes. So yeah, so this is a script. I clicked that script and it loaded it here, right? So maybe we can just go through this and just uh, see how to go about doing the actual mapping and how to, get around the region of interest and find out the geographic information or any other information you want. Then there is something called assets. Legacy assets. I'll just check what this is my name. And okay, these are the shape files of maybe the region of interest. You can probably upload the shape files and the map and all will be clipped as per your ROI because you are maybe particularly interested in a particular area. So as you can see this small red dot, so it is displaying that. So that's about, and this is a search bar provided at the top. This is about, so we have already seen 4 components. That is this map at the bottom in the editor screen where we actually put our logic. And this is for a display of your console, whatever you are printing or whatever you are writing to console, it will display here. On the left hand side, we have already seen we can have our saved scripts, assets, and all the functions which readily available functions which we can make use of. Okay. So now there is something called search places and data sets. Now all these data sets, how they are made available, you can just type. Suppose I want to type elevation, I'll type. So it will show me all the forms like tables, rasters. Basically all the data set will be available as a raster, all the imagery, satellite imagery. So suppose I want to click this shuttle radar SRTM digital elevation data version 4. I click this. Say here you can see it will show a display button import. So clicking on this import, it will automatically import your this data set for further processing. Anyway, I have already imported it. See here you can see imports one entry. So I've already declared a variable digital elevation model DEM, and this is the image. So if I had clicked on the import button, it will come like this only, right? So not only your data set, you can Sentinel, if you type Sentinel-1. Yeah, so you will see SAR, ground range detected data, C-band, synthetic aperture radar. So if you click on this, you have not clicked on import, you have just clicked on this thing. So it will display all the information about this data set. You can see what is the data set availability. It is available from 2014 till today. Then this is the description about the Sentinel-1 mission provides data from a dual polarization C-band. This is the whole information description about this data set. You can see here. Each scene was pre-processed. So as the Google Earth Engine servers, they also, not only they host the raw data, they also do a certain level of pre-processing on the data. Then you can see there are different tabs, bands. You'll have information about all the bands. HH, HV, VV. Basically, there are different types of polarization. Then image properties also. Okay, you can have different properties of the different images which you are getting, like start time and all that, a cloud cover, instrument mode, orbit number for particular scene. Every scene, every image, you will have properties, and these properties are also useful. Depends in your study. And there is, so we'll just close this. This is so now we'll go about and we'll see how do we actually map a particular data set, right? So we have here in a variable DEM image SRTM digital elevation data set. Basically this is the elevation model, and yeah, it displays you the ID. What is the ID of the data set? What is the type? It's basically an image. Then there are bands, list of bands, how many bands are available. Basically this is a single band image. So there will be, okay, these are image properties. Data type is there, coordinate reference system. There is elevation. There are you'll also get the min max values. Yeah, probably like this. So we have already stored in this variable this data set. Okay, so what we'll do right now, I'll comment the rest of the code. So one by one we will see. So you can use command and or control and question mark to comment if you're on a Mac or if you're on a Windows system. So basically we'll just print this data set and we'll see what is happening, what we have captured, what right. So we all know whenever we print something, it will come directly to the console. So I'll just hit run. Yeah, so it has printed here image one band. Same thing which it was displaying here also, right? So it was already available there. So when you print the data set, it will print all the details. This coordinates reference system is EPAG 4326, that is WGS 84. Okay. So now we want to visualize. So what we'll do is we'll add this SRTM data to the interactive map. Basically, whatever is available at this bottom is called an interactive map because you can interact with this. Because you can see here, right? You can see this mouse. You can create ROIs of your interest. Like if I click this, this is small ROI. Delete this. Yeah, so this is for zooming in or zooming out with a certain controls. You can even do full screen to this map. Okay, so we will what we'll do, we'll just call an add layer, right? You just type map dot and then do control space or command space, whatever you do. Yeah, control space. It will display all the functions supported by this map interface or this map. So we want to add an item. So what we'll do is we'll just add this dem. I'll just run this. Sorry, it's not add, it's actually add layer. So you have to add it as an add layer. The function is add layer, not add. So when you, okay, yeah. So in this layers here, you can see there is layer one. So basically this is this map which you have created, but you can see the visibility is like, you can see some dark or slight dark gray and dark areas, but you can't make out. So we'll improve this visibility of this. So what we'll do is we'll give some visualization parameters to the same, right? So earlier we had added add layer dem. Now we are adding dem min value, max value we are giving, and we are giving a name to this map. So now we'll again print. We'll just comment the previous one. We'll see after giving visualization parameters, how does it affect our visualization for the same data set. I'll just hit run. Yeah, so now it is much better, right? You can see this. So now we'll go to the console and just inspector, and I'll just click somewhere like the dark gray. I will check. Okay, so it shows me the elevation of some 1116 meters or something. If I click on some grayish area, dark grayish 985, if I click on whitish, you show me okay elevation. So whatever are the bright regions are the highly elevated areas. Like you can check out elevation 4389. When I click on dark gray, it will show 1120. Right. So that is how you add. This is about adding a data set to the map. Now we can further enhance this by adding colors also. Right. Just now we gave range of values, minimum 0 to, we just, for our visualization, we just considered whatever elevation was there between 0 and 4000. Right. So not only we gave visualization range, but now we are giving color parameters also. So map dot add layer, in this minimum 0, max 2000, palette green, yellow, red. Palette is basically the colors you can provide. So basically it will divide the full range pixel values between 0 to 2000 to from green to red in that order. So I'll just plot this and we'll just check how it helps to visualize in a much better way. Yeah. So now with just with one look, you can just see and tell it, okay, which are the most highly elevated areas. Like if you see this screen, the elevation will be going from green, yellow to red. So even the red areas will be the most highly elevated ones. 2157. So I'll click on somewhere on the yellow. Okay, 1103 meters it is showing. I'll click on green area. Okay, 534. So as you can see, starting from the first map, after that we added range of pixel values we were interested in, and then we added certain colors also. So now it is very evidently clear. We have an idea, okay, which are the elevated areas and which are the low elevated areas, right? So that is a small script that was based on, how do you use a map or there is something called so using DEM data, we can even use a server-side function ee.terrain.slope function. You can do this. You can see it will show. Select this, then dot again slope. You put this data, and so it will. The DEM data had all the elevated values at every pixel for the global scale. But now you will have when you plot terrain.slope, it will basically return the slope. It will give you an image. Slope will be this variable slope will be a type of an image which will not have elevation, but it will have the slope at every pixel. So if you want, we can just visualize again the same thing. So now we are plotting slope here, right? You can see here the item we are passing here. Earlier in the earlier commented code, we are passing them here. Now we are passing slope. So I'll just plot slope now. I'm interested in checking out the slope of a region. So I'll just very basic examples to just check how we can affect our visualization and use maps for better visualizations. Yeah. So you can click on a points green to red. So 8.9 for slope means it will be an angle or like slope or yeah. From green to yellow, yellow to red. Red is very red. Yeah, here you can see the red. 60. So it has a high value. You click on yellow, 33, and you go to green. So seeing this, you know what is the slope of every area. Slope is the angle. Elevation is okay, but what is the angle? So you seeing this diagram, you can have an idea of the slope of the territory, of the terrain. Okay, so this was about how do we map actually data sets, right? So this data set had only this SRTM data set had a data set which has only one band, and it was an image. So basically, in place of this, we can call an image collection also. There are certain image is a single image, but image collection is made up of a huge number of images. We'll be seeing it. So in this script, we just learned how to how to use the map object for our visualization. Now we may be going to so we'll just have a look at this. Then after this, we'll go for actual classification of an area. So there we'll have a greater idea how do we classify an area or a region of interest, and because classification itself is one of the could be considered as one of the methods where you have an idea of monitoring. Like suppose you get an image from 2019, you can classify your area of interest. You can calculate the area for all the classified classes, like this is forest and this much areas under forest, this much areas under the rivers or riverbed, or this much is under urban settlements. So doing a classification on a region of interest gives you an idea about the area if you have efficiently done the classification. So at different times of the year, or in different years, you can do classification and have a rough idea about what is the extent of a feature, like what is the area of a forest. That is in itself also is one way of indicative of like how much is the growth or how much is the shrinking in any of the features, land features or water bodies. Okay, so in this script we will be seeing something called, it is also related to the visualization. We'll understand something about true color composite and FCC, false color composite. What is it? So here you can see what I was talking about. Like if I type as Sentinel-2, right? So I have MSI multispectral data level 2A. This one. You can read about the data. We already went through this. So this data is already pulled here, right? You can see we have named this image collection S2. Image collection means there are a huge number of images. It is so huge that even if I want to print this S2 now, sometimes it returns an error because the huge number of, okay, it's computing error collection query aborted after accumulating over 5,000 elements. So you can get an idea that there are more than 5,000 images there in this one. So it's very important that whenever you are working with an image collection, you filter out the region of interest, you filter out the temporal range, and temporal range means you select the data, like you select the dates. Based on dates you access, right? Based on dates you can access from which date to which date you need the images, so that you can work on a particular area, or you can work on a particular aspect for that study. Okay, so here basically in this image collection, usually you'll see there will be images, and all the images will have certain IDs, but here we have already displayed one image with one known ID. So we are just utilizing this image for our this session. So we have created one image and we are already pulling this image. So this image is there with us. We are printing also. Now what we'll do is we'll just map this image just like we did true color, and we'll just analyze what is true color, right? Okay, we have already run this. I have already hit run for this script, so it has already produced all its outputs. I'll just hit again. Okay. So here you can see all the maps which you map or you print using this script. It will be displayed here in the order. So first we'll have a look at true color. Yeah. So true color map.add layer S2 image. We map this particular image, and bands. Earlier we saw a palette combination there, right? But there are two ways of passing visualization parameters. Either it can be colors. Mostly colors will work when there is a single band image, right? But probably this is not a single band image. I'll just check. Yeah, you see this print S2 image, print image details to the console, so that you can check the details of the image you are working on. So this is the image, this is the image ID, these are the bands list, B1, B2, B3, B4. You can see that there are 23 bands there, right? Properties, and these are the properties of the every image. So it is a multi-band image. So whenever we are dealing with a multi-band image, or whenever we are mapping it, we don't use palette, because palette is used for a single band image, so that a certain range of pixel values it can divide between colors. But when we are working with multi-band images, we supply visualization parameters in form of bands. B4, that is red, B3, okay, green and blue, right? So here the band sets are red, green, blue. Okay, B4, B3, B2, they are set in this order, because for normal human perception also RGB, they form the set of primary colors, and they make up most of our vision, natural vision for humans. So using these bands, we just plotted this and we named this plot as true color. So we'll be seeing this. This is the image. So if you actually see the image, or rather I'll use map so that it is very evidently. Yeah, if you see this image, it's pretty much resembling the natural look from a human's eye, right? You can see the greenery there. Most of the things are retaining their actual color or near actual color. You can see these are the river beds, and you can see what are the land areas and what are the covered under vegetation. It's very evidently clear. So basically this is a picture of a true color image, right? So you can print any data set in true color just to observe. You can pass the bands as B4, B3, B2. But usually what happens, you are using maps and in order to take out different studies and different expected outcomes from certain regions, we use different visualizations. One popular example is false color composite. What happens if I replace this B4 band, that is the red band, with B8, that is near infrared, and I have shifted all the bands. Like in place of B3 I have put B4, in place of B2 I have put B3. So what are these bands called? You can very well get to know from this. Like you open this, you will know. Yeah, here you will have, okay, B4 is red, B3 is green, B2 is blue, and B8 is near infrared. So we are generating the false color composite. So we'll just, and as I have already executed this script, I'll just load this plot from here. So you can see this is the false color composite. Yeah. So sometimes true color composite is the way we actually see the nature around, but sometimes using FCC brings out the more contrast between the features. Like now it's even more clear here, right? Compared to the previous vision, true color vision, which we had. Using false color composite, we can see all this red areas covered under vegetation, because vegetation is popular to, like, it's known that they have their major reflectance in near infrared. So it's a clear-cut indication, and it helps our visualization, right? So that is how we can form different combinations and just see which one affects our visualization and which one brings more clarity to the region of interest. So that is true color and true color composites and false color composites. Now there is something called NDVI, normalized difference vegetative index. So what here is we are doing is in the image object in the Google Earth, they have provided a function called expression, where you can, in this as a string, you can pass an expression, NIR minus red upon NIR plus red. This is basically an expression for calculating the index, normalized difference vegetation index. And NDVI is mostly used, or like it has extensive use in, like, it will tell you what are the green covers over a land area if you want to visualize that. So they created this variable NDVI where there, and not only you have to declare this expression, then you have to pass the values. RED is actually that band. Then if you do dot select, like you type dot control space, it will give you select. You can select this B4 band, that is red band. Then B8 is near infrared band. So you not only you declared an equation here, you also declared the variables for that equation. Red will stand for red, right? In additional parenthesis bracket here. Then so that product is computed in for the image S2 image, that is our image which we are working on. Okay. So now we'll print this. So it will print, okay, here it will show, it will have only one band now because it has done the computation. And early, you operated on S2 image, it had some 23 bands, but you did some calculation, but you didn't, but you saved it as a single band image. So this B8 will be having NDVI values. So based on these NDVI values of pixels, now it will be plotted. So we can again see So as you can see, Ni minus, as this is a ratio, it will tend to have a value between 0 to 1. Right. So I'll just remove this false color. I'll select NDVI because it's already computed in there. So I'll just plot and it will show us the plot for NDVI. Yeah, so this is a beautiful picture if you see. So if I click on inspector, if I click on green, I'll have a, okay, it is plotting a chart also. So NDVI value is 0.73 or something. I click on red. So it has a 0.021 value. So whatever it is shown in green, it is all the vegetation. Right. So seeing this, you can clearly make out, okay, what is the extent of vegetation over this particular region. Right. So this is another way of visualization. Okay. So we have seen what is true color composite, what is false color composite, and we have also seen how do we calculate a certain product or indexes. There are other indexes also, EVIA or other indexes like NDVI, which are useful for different purposes or different studies. Now let's quickly go to because I'll shift to another script area. Okay, yes. So by the way, all these details are also there in the same details are also there in the slide also. That's why I chose to work hands-on this. Okay. So here we'll be doing a classification on a region of interest. So we have our ROI also already saved here. You can see this is the ROI. So I clicked on that, so it will probably display it here. ROI Copernicus. Okay. The data set we are working on is Sentinel-2. It's optical data. Same data set we just saw in the previous system. So this is my ROI. So in this example, we will just see how do we go about supervised classification for a region. This territory will be classifying. Okay, so all these are the different feature classes, you can say. DBL, deciduous broadleaf, and EBL, evergreen broadleaf, ENL. These are further subtypes in the vegetation. Then there is Heptes, that is a kind of invasive species which is found to be grown around the features, linear features. Then there is a water body. Whatever water bodies will be there in this ROI will also be covered. And riverbed is there, non-forest shrubs. These are certain classes which will be dividing this ROI or classifying this ROI into, right? And then we'll be calculating the area also for all. Params FCC are the parameters for, these are the visualization parameters for FCC. Params TCC are the visualization parameters for TCC, B4, B3, B2 for TCC, and B8, B4, B3 for FCC, just we saw in a previous slide, same way. Okay, so just to save time, we have already collected the sample points from here. This is the, we have a training data we collect, like you can see right here. DBL we have 15 elements, EBL 15 elements, 15 small polygons we have created from each feature class, so that we can train our classifier with that training data, and can effectively classify this region and calculate the area for each class, like how much area is covered under riverbed, how much area is covered under water body. Okay, so after collecting all these points, what we are doing is we are not separately collecting data for training and for validation. We are collecting data at one go, and then we are dividing using a split variable. DBL dot random column. So you can see here, right? DBL, this each feature collection class, DBL, we are adding a random column, and then based on that random column, will be will that random column will be having a random value. Based on that, we will check split. If it is less than 0.7, put it into training, and if it is more than 0.7, put it into validation. So using that, we have divided our training data and validation data. Right. So okay, here we are using a Copernicus image also, that is to get an idea of what are the different kinds of subclasses present, like in a forest you can have, or what are the different kind of shrubs you have. So basically this was done, this additional image was used to utilize for that. So maybe this is currently not that much required. So okay, this is the code. This code here, we have collected all, we have divided the data. We have divided the data. Now we'll go about seeing, yes, here. Even this map also we will avoid, because we are not in the process of actually learning the different subkinds. We have already done that, so we'll just focus on our S2 data. Okay, here. So you can see the comments: supervised classification for November to December. We are targeting a few November and December selection. Okay, so S2 is the image collection, which you can see at the top, right? This is the image collection already fetched with huge number of images. So what we'll do is we will filter bounds. There is something called filter bounds, and we'll pass our region of interest. So all those images which have fully covered this ROI or have any overlaps over this region of interest will be filtered for our study. Okay, so implementing that, after that we implement filter date. So we pass the date also in this format, like 2020 November 1st to 2020 December 31st. So probably in a stretch we are taking 2 months here. We are filtering all the images with this temporal snap signature. So all the images taken between these 2 months will be utilized here. Then we have some filter metadata where we have cloud pixel percentage. Maybe we want least cloudy images, so we are passing a value here. 2%, less than 2% will be good for our study here, right? So what we all do, so when you run this particular code runs, this selection will, one variable will have a list of images. So what we'll do is for classification, you cannot do a classification on a multi, you cannot do a classification on a, for classification, you have to have a mosaic, you have to have a composite basically. Like, so what we do here is we use mean. So at every pixel for all those images, we'll have a mean value. Then we'll do classification based on that mean value. There are other functions also that depends on what kind of study you are doing, right? Like you can have a median also. What is the most recurring? What is the value which is most recurring on that particular pixel in that particular time period? So maybe we'll utilize the mean for now, right? So this is our main image, mean one. Then as it is a multi-band image, we are only selecting our interested bands where we are interested in: B2, B3, B4, B5, B6, B7. So all these bands will have a resolution of around 10 to 20 meters. So that is a good resolution. Other than that, there are some 60-meter bands also are required for some ocean or weather studies. Maybe may not be that suitable for our study. So we are doing that. Then we are doing clip over ROI, our ROI. So this bands one image will be there. Okay. So here you can see we are printing, we are mapping bands one. Same image. This is our main image, which we will be working with bands one, which we will be classifying using our training data here. This data. And this data we have divided into training and validation also. Well, using validation, we can see what is the accuracy and how much accuracy of the classifier for predicting the class, right? So what we'll just have a look. There is some of the code which I have commented, which is not useful for this session. So this bands one is the final composite which we have created, selecting our relevant bands and clipping over our ROI, right? So This bands one is plotted as both TCC winter and FCC winter. Maybe we can have a look at it. I'll just run this, and it will generate all other plots also, which we have not covered so far theoretically, but I'll just uncomment that and we'll go through that. I'll just click run. I've hit the run, so it is, you can see here it will load layers. Yeah, slowly it will load here in the bottom. By the way, all this code is available at developers.google.com also. What is supervised classification? What is unsupervised classification? Basic difference is unsupervised classification means you just run it and it gives you clusters. It will give you different classes. It will club all the pixel based on the similar values. It will create different classes and give it to you. But in supervised, what you are doing is you are giving a training data. So you are feeding it with a prior information that this class, this data set belongs to this class, like that. Yeah. So you can see here we have already mapped that one final image which we created, right? We clipped over the array. This is that true color composite for that image, and this looks very familiar to the true color composite which we have seen in the previous script, right? So you can see here. So as you can evidently make out seeing this image, what are the rivers, what are the area of rivers, what are the forests, and what are the settlements, even settlements also you can see here, right? So it is so far so good. Like in TCC, you can make out what are the features. Now we have also printed the FCC. We'll just have a look at the FCC also. What is the kind of picture we are getting, so that we can, yeah. So if you see, this is the FCC of the false color composite of the same ROI. So this also brings out very contrasting visualization, right? You can see what are the settlements. Settlements are all there in the white, and the river water body is there in the bluish. So I'll just, I have zoomed in. I'll just go out. So this is our main ROI and main composite where we are going to do the classification. So now how do we go about classification? What we do is we create a variable called training points, right? So now all the classes which we have created, we have to merge all the classes like DBL, EBL, ENL, HIPTIS, water body, riverbed, non-forest, shrubs, right? We are adding all the training points. So here we are just simply doing merge. You can see this dot merge this training. So we have created something called riverbed training, riverbed validation, non-forest training, non-forest validation. So there are pairs. So we are creating training points. That's how you create training points. We have merged DBL training, EBL training, all the samples collected with training. We have merged to create a cumulative training points data. So now what we'll do is we are creating a training data one. What do? We select that image and sample regions, our training points, whatever variable we have created about training points, we have passed here, and we are giving a properties. So when we create a, if you see here, no, these in the bottom, if you see geometry, these are the feature collection we have created. If you select one, there is a property called PSC. It could be land cover also, anything you can give, like land cover. Based on what it will be classifying, you have assigned a value of 0, right? So the other one will be having a value of 1. So suppose you have 10 classes, so you will assign a value to each class, 0 to 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. So we have and that value has a label called SC. So we are passing to this image and sampling our region based on these training points. Property is SC. So based on this property, it will, you know, train this. It will create this training data. That this training data has to focus on this property of all the classes. Then the scale is 20. That depends on your resolution of your data set, like what scale you want to set. Okay, now we create a variable called classifier. So we have fixed our training data. We have our training data. Now we use EE functions dot classifier. We create a most very popular classifier that is called random forest. So these are inbuilt actually. If you do ee.classifiers, capital C, LA, control space, you will get classified. Yeah, this train. So you have to go to classifier class, then you have to assign a classifier. There are number of classifiers here. Decision tree, smile cards, name, random forest, spectral region, gradient tree boost. So depending on your study, you can choose what is more relevant for you. So random forest is pretty popular. With as a parameter, you can pass some number of nodes here, and dot. Then you call dot. Then that will give a function called train. In that train function, there are two parameters: features and class property. So features, you can pass your training data. Class property is SC, right? So this is how you train your classifier. So your classifier is trained here in this piece of code here. Anyway, this whole piece of code is also available at developers.googles.com. You can refer there anytime. You can copy and just execute. May not this code, but you will get a generic code there available, because this is something based on our study which we did in IIRS. So now we are creating a classified image, means we are classifying this ROI here based on our, and how these sample points were collected was either you can go to a field physically and take your GPS receivers and trace the coordinates and bring them back in a format like KML or something. But here I think you can see here we have used this Google map itself to plot these. Like if I want to see DVL, I think I'll be able to see these are the polygons. Can you see? I'll change. See this green small polygons. These are created here itself. So these that's how you visually go to different areas and create polygons and save them as a data point for uh, this particular class. Just a minute. Just a minute. Okay, so yeah, I know, it's fine. Yeah, so you can visualize all other points also. I hope you are able to see. I'll mark the ROI also. Yeah, here inside this ROI. Yeah, here you can visualize all these sample points taken. Can you see? Right, so that is how it has been done for this. Now after that, our classifier was ready here in this piece of code. We have trained our classifier. We had our training data. Now we'll just simply use a image. The image actually, the image function, the image class gives so many functions like classify. So you just have to type .c and control space. It will give you a classify. You have to pass your classifier here as a parameter. So it will utilize this image, will utilize this classifier function. It will utilize this classifier. This classifier is in turn utilizing this training data, which you have training, and this training data variable itself has training points, which you have marked here and we just saw here. So based on this training data, it will classify the image and you map this image. Map.add layer, classified image, palette. Now, this is a classification image. So it will be a single band image. Now you are giving colors, okay? A variety of colors you have given, because you are apparently expecting some 1, 2, 3, 4, 5, 6, 7, 8 features to be classified, right? You are expecting this region of interest to be classified into 8 classes. So you are giving 8 distinct colors. Max minimum value 0, and we'll just see LULC, land use land cover winter. We'll just see what is the map. So it is here LULC. So we'll just see. We have already run the script once, so it has already executed. So this is the classification it has given. So you can see. So whatever is this dark black in color, no, it is the invasive species we are talking about. If I click on this, I'll have some value here. So based on that, you will get to know, okay, what is the, see, so it is giving classification 3, LULC winter classification 3. 3 means 0, 1, 2, 3. 0, 1, 2, 3. So it is HIPTIS. If you click on green, even somewhere you click, it will give you a classification class number. So from that you will get to know, okay, this it is that feature. It is DBL, ENL, right? So basically, this is you classified a region of interest utilizing training data. And here it looks like. So basically, this study was done to find out the growth pattern of invasive species. That is this black color. But it utilized machine learning algorithms like random forest for classifying the image in a supervised manner. Supervised is when you give a training data to it, right? So that is our major first step. Like we have already classified it. Now what we are doing is you can even calculate areas for each class in a winter image, like whatever you have classified, right? So you can classify what is the area falling under each class. So this code also you can get on Google, developers.google.com. You simply do ed image.pixel area dot add bands. So in the add bands, you just add your classified image. So you have created an area image, right? Print area image, so it will print something to you. But it will not print in inspector, it will print in console here, right? So then you create another variables called areas. You use this area image because it will have this classified image full area dot reduce regions. Reduce is a function like you can reduce based on different properties. E dot reduce dot sum dot group field name, group name class, because then geometry of the ROI you have to pass, scale and maximum pixels 10 to the power 10, print areas, and it is printing the areas also here. So in this class areas variable you have created, basically this is most of the code here is to sort the visualization. Basically here class areas list. So here it will class number area get sum dot divide by 10 to the power 3 dot round. Then this list will be created. It will give you a tentative area in square kilometers 230. Okay. So class 0, class 4 was our class 3 was 50, I guess 28 square kilometers. So this is in square kilometers, the area given for all the classes you have classified. So like you can choose different time periods and different different temporal images, and you can find out the areas based on classification. Also you can have a rough estimate that okay, what is the growth or what is the what is the expansion or what is the contraction in the features, land features, or any specific land feature class you are interested in. Okay, now this was it, but we have already divided our training in training and validation, right? So here is our validation. Similar to training points, we have merged our validation points also, right? Now what we'll do is similar to our training data, we created a variable called validation data also. Sample region, same validation point, but we are using a different seed here. Where is it? Okay, this is validation data. Yeah. So now our validation points which we created from half we split, right? In the beginning we collected whole data set, then we divided into validation and training, DBL training, DBL validation. We merged all DBL validation as a validation points. Then we pass these validation points to our classified image, whatever we have classified image one, this at the bottom. We pass sample regions, we pass the validation points to it, same property, same scale, and we just print test accuracy. So in that what happened, validation data dot error matrix we print. So it will print a error matrix based on classification, this classification band and this SC band. So this SC band is the band going with the validation data set, classification is the data set in the classification image, right? Classification image utilized training data, and it divided the features based on a band because it is a single band image, but it named that band as a classification band. So classification value will be 0, 1, 2, 3, 4. So now we are checking error matrix using our validation data, right? So somewhere it will be there. This is the, yeah. So we are checking what is the error matrix when we gave the validation data to the same classifier. So here we can see 0. 0 is the first class, 185 pixels assigned to the first class, right? Second class. So maximum number of pixels are assigned to the second class. 0 in the first class, 44. 1. 2 means 279 pixels. So it is comparatively consistent, right? So this, seeing this matrix also, we can get an idea whether our classifier is getting confused, right? Whether our classifier is classifying a certain class points into another class. So having a look at this confusion matrix, error matrix, we can have that idea. Now, after creating this error matrix, we can print the accuracy also. This is overall accuracy, 0.80, then that is 80% something. So what is the accuracy of our classifier is 80%, around 80.7 something. And there is something called coefficient called kappa, which is calculated overall, and it comes around 75% something, which is a fair value. Like kappa coefficient has to be between 0.75 to 0.9 or 0.99 something. That again depends on the study. So that is how you test your classifier. So in this script, we just did a classification of a region, right? We calculated area for each class. Then we also collected sample points from using Google Earth Engine here. And how do we do this? I'll just like I put a point here. See this green point. So this green point here. Anyway, it is going into e-bill class right now. So I'll just undo this. That is how you select points. It's easy only. So the purpose of this script is so much solved further that you can classify using supervised classification. You can calculate areas, so that can give you an idea into forest monitoring. If it is about forest monitoring, you can calculate the area for the forest, right, or a specific vegetation inside forest. Or so with this, we are actually done with the major portion. With this script, we know. Then there is we can move back from here, like whatever demo was to be covered on the Google Earth Engine. This is I think so far consistent with the presentation. We can now move back to the presentation. What actually is more is there. So this is about the code and code editor. I have already told you what are the components and all, right? These are the data sets. That visualization also I have already informed you. Then there are ready-made codes available also on the developers.google.com. You can go there. And as far as monitoring is concerned, we can do classification, calculate area class. Then there are other methodologies also to calculate forest monitoring. That is, there's something called time lapse also. Time lapse link is there where Google has stored around 40 years data, and it will create a GIF, and you can you can see like a movie. It will go and it will here time lapse Google Earth Engine. You can just put time lapse in Google search bar, and you will get this link. I'll just go there and we'll just have a look at this video. Google Earth Engine. So a broad level of like a very superficial way of monitoring, you can go through this. You can see this Colombian glacier retreat mining area. There's so much. I'll just go to. I'm just typing some location, some geographic location you can enter, and see, you can see here data is there since 1984 till 2020. And if you play this, it will play as a video file, like as a GIF. It will play and it will show you the progress or expansion or contraction of all the features, geographic features. It will display. I think it's already started. My machine could be a little slow. Okay, I'll just zoom out a bit. Yeah, let it load. Let me play it again. machine could be a little slow, so please excuse this. I'll just switch off the Google Earth so that I'm not sure. Yeah, there's some visuals which are maybe it's, but you can try this link out and you can visualize for yourself how it is changing over the years. You know, the forest and all. See here it is changing the year. So this is a very like uh, one superficial way of monitoring for a huge data over years from 1984 onwards till like how a particular region has been changing in terms of land cover. Other than that, for monitoring, there are other tools utilizing Python and all. Basically, like you calculate change over a certain ROI using certain satellite images for a given temporal images, but that goes under some change detection problems. You can also utilize that and create a product for forest monitoring. So I think with our time, I'll just stop with that. So that was all for today from my side. I hope you can go through this link, time lapse link, on your own. Just type in Google time lapse and it will come. Yeah, that's it. You just click here and you will be there. So thank you. That's all from my side. Thank you.